At Edwards Air Force Base, California, a contractor-designed rocket sled was used in rain erosion tests. The purpose of the tests was to evaluate the effect of hydro forces upon plastic radomes and other materials traveling at high speeds. The vehicle is an 800-pound rocket sled propelled by 7 solid-fuel JATO bottles. Each of these solid-fuel rockets delivers a thrust of 11,000 pounds for a period of 2.2 seconds. Object of the tests was an F-102A radome. The nose probe was shortened for the runs and shaped at the tip with a 1/4 scale model of the radome using the same materials. Sprinkler nozzles were placed along an approximately 2,000-foot section of the 10,000-foot track. By this means, simulated rainfall was directed into the path of the rocket sled and regulated to a rainfall rate of 8 inches per hour. A booster sled, propelled by 5 of the JATO bottles, is used in initial acceleration of the vehicle. During the June 18, 1956 test run, the rocket sled attained a speed of 1,623 miles per hour, equivalent to Mach 2.085 at this altitude. On June 19th, a second run was made. Motion picture footage was shot at a speed of 128 frames per second, giving a good indication of the sled's speed, which was better than 5 times that shown here. During this run, the sled attained a speed of 1,670 miles per hour, or Mach 2.115. This run set a new world speed record. The rocket sled is braked at the end of a run by means of a standard water brake. A scoop mounted beneath the sled travels through the water troughs in the braking area. Following the tests, materials subjected to the rain erosion were thoroughly analyzed to determine their ability to withstand these forces in operation. After all runs, material at the tip of the nose probe was found to be significantly affected, demonstrating, by use of the radome scale configuration, what might happen to the radome without the nose probe. Radome materials held up well under the high force loads, partially because of force dispersal by the projecting probe and the subsequent shock wave formed thereby. With the longer probe, this protection would be even greater. From the results of the tests, engineers were able to conclude that the radome could be flown through approximately 10 miles of 1 inch per hour rainfall at a speed of Mach 2.0 without significant structural damage to the radome. At the contractor's San Diego plant, construction of the F-106A, formerly termed the F-102B, is progressing in 4 stages. Fuselage construction of the number 1 flight article was 45% complete as of July 1st, 1956. Of the 4 fuselage sections under construction, 2 are being built as flight models. 1 will be used as a control systems test stand, and the 4th will be used as a power plant test stand. These sections are located in the experimental building. The F-106 canopy, similar to the F-102A canopy, has been constructed to withstand higher stresses and is to be subjected to a series of static and repeated load tests as a part of the complete test program. Wing sections being built in the production area of the plant were well underway as of the July date. Upon completion, the wing sections, essentially all fuel tank, will be used in flight models, in control systems tests, and as fuel tanks in a test program designed to prove out the 106A fuel system. It is anticipated that performance characteristics of the F-106A will be significantly greater than those of the prototype. Tests have been made on an F-102A with an increased vertical fin area. This modification was brought about because of pitch roll coupling encountered on another Century Series fighter, and accelerated because the problem was encountered in flight tests of the YF-102 and YF-102A. Production models of the F-102A have a vertical fin area of 68 square feet. A side slip feedback to rudder system was installed, freeing the airplane from pitch roll coupling effects that exceed the structural limits. Flight tests were then conducted on the F-102A airplane with a 95 square foot vertical fin area. The tests demonstrated that the big tail airplane was completely free from the effects of pitch roll coupling. Production models of the F-102A with a side slip feedback to rudder installation can well perform the interceptor mission for which it was designed. However, the F-102A with a 95 square foot area vertical fin embodies in the primary structure of the airplane adequate directional stability to be completely free from the effects of pitch roll coupling without the use of artificial augmentation. The larger vertical fin will be installed on all aircraft now in production. 37 F-102As at Holmdel are to be retrofitted. Plans include the modification of the first 25 F-102As delivered to the 327th Interceptor Squadron at George Air Force Base. At George Air Force Base, California, Air Force pilots are receiving initial training for the F-102A Interceptor in a Link F-102A simulator. Procedures and techniques required to fly the F-102A on tactical missions are taught by use of the trainer, which, through instrument indications, electronically simulates flight characteristics of the airplane. Pilot trainees sit in the stationary cockpit, which is essentially a duplication of the F-102A cockpit and controls. An operator's flight console contains instruments and controls which set up flight problems and repeat instrument indications observed by the pilot. Flight conditions, including load factors, may be simulated by means of this panel. Switches are included which may be used to introduce operational failures which could possibly occur in a modern high-speed interceptor. The instructor's position is beside the simulator, where he can visually direct and observe the pilot and console operators. During a radio navigation problem, the position of the fighter with respect to the ground may be determined at any instant by means of a ground position recorder. A standard aeronautical chart is attached to this instrument, and the course flown by the pilot is plotted on the surface of the chart. The operator's radar console is used to set up a target problem for the pilot. Target attitude is established here, and a radar scope monitors the picture received by the cockpit scope. Jamming of the cockpit radar scope may also be accomplished at this station. The integrator console contains the two ground position integrator computers and the altitude integrator computer, along with associated controls. At this console, the target and fighter may be placed at any desired position on the ground position recorder. All consoles are interlocked to function as a unit. Following their training in the simulator, pilots may receive extensive training in the TF-102 airplane, trainer version of the F-102A. Then they are ready for their first solo flight in the F-102A. Use of the simulator facility will provide for thorough, intensive instrument flight training of a specific nature for F-102A pilots. George Air Force Base is the home of the 327th Interceptor Squadron, first operational squadron to receive delivery of 102 airplanes. As of July 1st, 1956, 5 F-102As and 1 of the TF-102s were based here. More are scheduled for future delivery. With the activation of the 327th Interceptor Squadron and activation of other F-102 squadrons scheduled for the near future, training of pilots for flying the high-speed, high-performance airplanes takes on greater significance. The increasing complexity of modern aircraft is putting greater demands upon skills required and upon the training program aimed toward perfecting these skills. 327th Interceptor Squadron pilots, upon completion of their training, are presented with the emblem of their craft. A contractor service engineering representative was on hand to make one of these presentations, initiating another pilot into the growing number who wear the Delta pin. Holloman Air Force Base. Further testing has been accomplished on the MB-1 air-to-air missile. In prior tests, the 1781 airplane, a YF-102 with a fixed pylon launcher, has been used in determining what problems might be encountered because of blast or temperature effects upon the F-102 airframe. 8 aerial firings using the 1781 airplane as the test vehicle were completed as of July 1st, 1956. Test results were satisfactory, revealing no significant effects of blast pressure or temperature upon the airplane. Paralleling the contractor's program, studies were made of the missile trajectory patterns. Test altitudes ranged from 20,000 to approximately 45,000 feet at speeds of Mach 0.79 to 0.97. Current phases of the test program are developmental in nature and involve the use of 2 F-102A airplanes. One of these, the 1797 airplane, carries the missile within the missile bay and fires it from an extended rail launcher. The other F-102A, the 1806 airplane, features a ballistics missile ejection system. This system has been tentatively approved as the installation to be used in the F-106A and is the alternate system being considered for production F-102As. Flight tests with 1806 have been limited to testing of the ejection mechanism. Of major concern in these flights has been the timing sequence for rocket igniters, which must be held to critical tolerances. 6 of 12 scheduled ejections have been completed. Further flight testing has been discontinued until production rounds become available. The 1806 airplane has been returned to San Diego for installation of the fire control system. A decision between the 2 methods of launching the MB-1 from F-102As is pending completion of the test program. In addition to aerial ejections, test firings of 3 MB-1 missiles from an ejection test stand are scheduled for the future. At Holloman Air Force Base, New Mexico, the F-102A was used in a program for development of the Falcon missile weapons system. This armament is carried within the missile bay and extended into firing position when ready for use. During these tests, missiles carried telemetering equipment in addition to the normal fire control system for instantaneous recording of test factors. First firings were at parachute targets and were instrumental in developing the weapon system toward the program objective. That is, the functional efficiency required for scheduled salvo firings of tactical missiles against a co-altitude target. In the tests, improper design features were discovered and intensive work done toward perfecting the system. Development was necessary on the radar vectoring system, missile and fire control electrical systems, launcher valves, telemetering equipment, and the Missile 106 box. A firing at the drone was accomplished on May 10th without missile warhead. A hit was scored on the vertical fin of the QB-17. A salvo firing of tactical missiles was accomplished on June 5th, and the target drone demolished. The kill occurred over the Gulf of Mexico. The purpose of the tests was to evaluate the effect of hydro forces upon plastic radomes and other materials traveling at high speeds. The vehicle is an 800-pound rocket sled propelled by 7 solid-fuel JATO bottles. Each of these solid-fuel rockets delivers a thrust of 11,000 pounds for a period of 2.2 seconds. Object of the tests was an F-102A radome. The nose probe was shortened. At Edwards Air Force Base, California, a contractor-designed rocket sled was used in rain erosion tests. Is used in initial acceleration of the vehicle. During the June 18, 1956 test run, the rocket sled attained a speed of 1,623 miles per hour, equivalent to Mach 2.085 at this altitude. On June 19th, a second run was made. Motion picture footage was shot at a speed of 128 frames per second, giving a good indication of the sled's speed, which was better than 5 times that shown here. During this run, the sled attained a speed of 1,670 miles per hour, or Mach 2.115. This run set a new world speed record. The rocket sled is braked at the end of a run by means of a standard water brake. A scoop mounted beneath the sled travels through the water troughs in the braking for the runs and shaped at the tip with a 1/4 scale model of the radome using the same materials. Sprinkler nozzles were placed along an approximately 2,000-foot section of the 10,000-foot track. By this means, simulated rainfall was directed into the path of the rocket sled and regulated to a rainfall rate of 8 inches per hour. A booster sled, propelled by 5 of the Jato bottles,